Again, looking at the normal distribution, again, we had mentioned that it is the most commonly known distribution. It has a bell curve shape. It is a continuous distribution. There are two parameters associated with it, the mean and the standard deviation. So when we describe a normal distribution, we're always going to describe it as with a mean and as having a mean and a standard deviation. 68% of the data lies within plus or minus 1 standard deviation, 95% of the data lies with plus or minus 2 standard deviations, and 99.7% of the data lies with plus or minus 3 standard deviations. When referring to these distributions, we want to carefully look at the curve and the area under the curve. Now, you might remember from calculus that a curve can be described as the area, or can be described by the area under the curve. So for probability and statistics, this is an essential point. Consider the curve on the right, where we have a normal distribution with a mean of 0 and a standard deviation of 1. The entire area under the green curve has a value of 1, and the mean line, the dashed line, splits the distribution into two parts. The left side is 50% of the curve, and the right side is 50% of the curve. So again, if we consider that our probability was always from 0 and 1, we now have a relationship here to these normal probability distributions that say if the event is not likely to occur at all, it's 0, and if all of the events are likely to occur, and then it's 1. And that's why we focus on the cumulative distribution. In the normal distribution, the mean and the median are theoretically the same. So this should be apparent from the graph here on the right. Since 50% of the curve is to the left and 50% of the curve is to the right, the 50% would represent the median. And because our mean is on that line, the two are identical. So this function, the function that provides the probability distribution of a continuous function, is called a density function. In the normal density function, it's a continuous distribution, which means that the possible x values range from negative infinity to positive infinity. And that's what we have on the bottom curve at the bottom. Consider human temperature example on the right. It's well known that the mean is approximately 98.6, but it is certainly possible that someone's temperature is less, significantly less. But what are the chances of that? They get very, very remote. If we look at the curve, the probability of having a human with a temperature of less than 96 degrees is possible, but highly improbable, confirming something we somewhat already know. Now, the normal density function, as we said, is what describes the normal curve, is described by this function below. And it's not really important to know because most of the statistical software in Excel will do this for you. But it is interesting to note that it has this constant e in the equation. And e is the base of the natural logarithm, which we see in a lot of mathematical formulas and financial formulas as well. One of the things that we like to do with the normal distribution is we like to create z-values, these things called z-values. The ubiquitous nature of the normal distribution makes it appealing. We can use it in a lot of different things. And it will have the same bell shape to an extent, but it can vary. The differences in the shape will be based on the standard deviation of the curve. So as the standard deviation changes, you'll see certain parts of the normal curve show a little bit of different characteristics, such as fatter tails or wider dispersion. Now, the chart on the right here represents a standard normal distribution, and the reason it's called standard normal is because it has a mean of 0 and a standard deviation of 1. And the reason this is important is because we can actually use this distribution to explain any other normal distribution. We can standardize it and then create these z-values. And this allows us to do a comparison between two things that may not seem to be equal or may not be easily comparable. So, in this case, the standard normal distribution is mathematically denoted as n0, 1. That means it's a normal distribution with a mean of 0 and a standard deviation of 1. Knowing this, we can take normal random variable and standardize it by creating a z-score or a z-value. The z-score is easy to calculate because all we need to do is take the value of the random variable, subtract the mean from it, and then divide by the standard deviation. When we do that, we get a z-score. So let's take a look at what this is. Why is this important? Well, suppose we have a set of data on the right. We have sales of a given set of customers. We can calculate its mean as 41.97 and a standard deviation of 28.50 in Excel easily. To calculate the z-score, we're going to use the following formula. Z equals x, we take the x value, which is the total sale, subtract the 41.97, and then divide by 2850. When we do that, we end up with 1.346 for the first entry. The reason this is important is because now this can be interpreted as 1.346 is 1.34 positive standard deviations away from the mean. The second row is interpreted as 0.1353 standard deviations from the mean. So now we know where it might lie in terms of the distance from the mean. Now, in Excel, we can use the standardized function to get the same value. It already provides it for you, so you don't need to use the actual formula. But it's important to understand where Excel is getting this from and what the principle behind it is. Given the fact that we have a z-score, we can calculate the cumulative probability of the z-score. Remember that under the normal distribution allows us to find the area under the curve. The graph below shows the area under the curve where the z-score is 1.3464. How much area is under the curve? So if we have the z-score of 1.364, we know it's 1.364 standard deviations away from the mean. So we want to calculate that whole area to the left. Now the way we do that is we take the z-score and we put in NORM.S.DIST. When we do that, we end up with a value of 0.91. And this means that 91% of the curve is to the left of 1.3464. So we can also attribute this to being in the 91st percentile. If you compare the total sale, 80.34, against the mean, 41.97, it's clear that it is far to the right, and a majority of the numbers will therefore be on the left. Now, in the prior slide, we saw how to obtain the probability of a z-score. It's possible to conduct a reverse procedure. Assume that we want to know the z-score from a probability of 91% or 0.91. We can actually use the reverse. So we will do NORM.S.INV with the probability. So if we put in the 0.91 as the parameter, it will return 1.3464. And what this basically says is that if we're looking for the 91% cumulative probability, the value is going to be 1.3464 for the z-score. We can then use that to calculate what the total sale would be at that 91%. Previously, we saw how we can obtain the probability given a z-score and a z-score from the probability using the NORM.S.DIST and the NORM.S.INV function. We can use similar and alternative functions to obtain the probability from the actual value directly. The S in the Excel function stand for standardized. So the normal standardized distribution, normal standardized inverse procedure. In the total sale to the right, we can obtain the actual value from a given probability. In order to do this, we must first know the mean and the standard deviation just as we had before. So given the mean 41.97 and the standard deviation, in order to obtain the probability, we would do NORM.DIST of x. We provide in the x value, which is the total sale, which would be 8.34. We put in our mean, 41.97. We put in the standard deviation, 28.5, and true for the cumulative probability. So that true is going to basically say, give us the cumulative probability. When it does that, it gives us the cumulative probability of 0.91. We can invert the procedure as well by saying NORM.INV to actually get us the 0.91% area under the curve, given a mean of 41.97 and a standard deviation of 28.5, and you can see that it will return 80.34. We can also have a little fun with the normal distribution because what we can do is we can find the area of the curve in between 2 points. And we might want to do this to find out, okay, well, what is the area along underneath the axis that's going to give us that from -1 to 1 z-score? If we wanted to find the area under this curve, we could do that. What we would do is we would do our NORM.S.DIST, again for the standardized, because we're using a z-score of -1, and that's 0.159. That area is calculated and given by the orange shaded area. If we calculate the area of the curve to the left of the z-score plus 1, it would include the area in blue and orange and give us the following result. When we use NORM.S.DIST 1 and the cumulative probability true, it would give us 8.841. Thus, it will give us the whole area, the blue and the orange. But if we subtract the 0.84 from the 0.15, that would give us just the blue area, which actually equals 0.683. And what's interesting is that we had said we were looking for a z-score of -1 to +1, and those would correspond to the standard deviation, as we said, of -1 and +1. And we could see that 0.683 is about 68%. And therefore, if it's 68%, that's what we had said before as our rule for one standard deviation. So this is how we can calculate in between certain areas. And it can be done instead of using the normal standardized functions, we could also use the normal functions with the actual values.